Welcome to the fifth lecture on the course Applied Stochastic Differential Equations. My name is Arno Solin and I'm the second lecturer on the course. The contents of this lecture are as follows. First, we will go through a short introduction to the topics of the lecture. After that, we dive into ordinary Runge-Kutta methods, which are for ordinary differential equations. Then we have a look at strong stochastic Runge-Kutta methods. We cover weak stochastic Runge-Kutta methods. And finally, we summarize the lecture and go through the topics as a whole. We start with the introduction to the topics. First, we go through Runge-Kutta methods for ordinary differential equations. These methods are based on Taylor series, and they are general in a sense that they can be applied basically to any ordinary differential equations of a suitable type. We shortly discuss explicit and implicit schemes and go through some basic methods in ordinary Runge-Kutta methods. After that, we dive into the stochastic counterparts of these methods and start with so-called strong Runge-Kutta methods for stochastic differential equations. These are based on the Ito-Taylor series. As you saw for the regular Runge-Kutta methods, which were based for the Taylor series, so now we are working with Ito-Taylor series in this part. We go through a family of strong order 1.0 schemes, which we show some examples for, and also discuss the problems related to the iterated Ito integrals. In the last part of the lecture, we have a look at weak stochastic Runge-Kutta methods, and more specifically, we take a look at a family of weak order 2.0 schemes. For the weak methods, we have means of approximating the troublesome iterated Ito integrals. Don't worry, these topics will be clearer towards the end of the lecture. In order to give you a background in Runge-Kutta methods, we first go through some plain ordinary Runge-Kutta methods for ordinary differential equations. Runge-Kutta methods are a family of iterative methods for solving differential equations. They are based on Taylor series, which Professor Särkkä covered on the previous lecture. But they are derivative-free, which makes them easy to use in practical calculations. That means that they are so-called plug-and-play methods that only require specification of the differential equations. Well, at least in the ideal case. There are other methods as well, which are not considered here on this lecture. For example, so-called multi-step methods, multi-derivative methods, higher order methods, or then methods tailored for some specific problems or structure of the model. Let's start by considering a simple first-order nonlinear ordinary differential equation. The simplest Runge-Kutta method is the so-called Euler scheme, which has been covered on this course already several times. It is simply based on sequential linearizations of the ODE system. This method is easy to understand and extremely easy to implement numerically. However, the global error of the method depends linearly on the step size delta t, which means that this is not the ideal method for practical use and calculations. Let's extend this a bit. The ODE system in the previous slide can be integrated to give the following. Now, recall the previous lecture where we used Taylor series for expanding the equation. Now we get the series expansion of the following form where a couple of the first terms have been written out. Here the series expansion has been given in terms of the linear operator L. In other words, we get a series which looks quite complicated and gets even more complicated when you keep adding terms. However, now if you take a close look at the first row, you recognize the simple Euler method there. Now we wish to make higher order methods by including more terms from the Taylor series expansion. For the sake of simplicity, let's consider terms up to order delta t squared. This already makes the expression look quite more complicated. And now we are left with a set of derivatives in the expression. In order to make a derivative-free method, we somehow need to get rid of these derivative terms of the function f. That means that we seek a form of an iterative scheme with an extra stage, here denoted by blue, where a, b, c and d are some unknown scalars. In the last term, we can consider the truncated Taylor expansion, that means a linearization, around the function f evaluated at a given point. This means that we get the following expression for the blue part above. Combining those two expressions, we get an expression of the following form, where we see that we have the constants a, b, c and d now in those places, and comparing these two expressions on the previous slide, we can now get values for a, b, c and d as follows. Solving this gives us a derivative-free method which has two stages, and this method is known as the Heinz method. This was already covered in the introductory part of the course material, but now it was derived by considering terms of the Taylor series up to order delta t squared. In this method, the finite differences for the derivatives are considered by truncating the series expansion, and this method is of order 2. In general, Runge-Kutta methods are often presented using a special sort of table. This makes it handy to avoid the lengthy sum equations and series presentations, and instead show only a table with a number of values. In the following, we will go through some quite commonly used Runge-Kutta methods for ordinary differential equations in the form of these tables. These tables are called the Butcher table, and this definition of the algorithm on this slide gives an overview how to use it. However, it might be handier to check that in the course material. Just to give you a picture of how the tables look like, I will now go through a number of methods. So basically the table has three parts, defining some values which are basically put in a matrix A, in a vector C, and in a vector alpha. The simplest method is the plain old Euler scheme, the so-called forward Euler method, which has a very simple Butcher table. The classical, very well-known fourth-order Runge-Kutta method has a slightly more complicated table. This method is presented also in the introductory part of the course material in a different form, but in this chapter the table formulation will be used. In addition to so-called explicit schemes, also implicit schemes exist. I will just very shortly cover what this means in order to give you some sort of backdrop for this part. Even though the Runge-Kutta methods try to be very simple plug-and-play methods, in practice, which method to use depends on the problem. Especially difficult the use of these methods comes when the solution includes some rapidly varying components. These problems are often referred to as stiff problems. And in the case of these explicit schemes, you would need to use an extremely small step size in order to keep on track when simulating the solution. So in practice, quite often the solution trajectory simply explodes at some point, and you get nonsense out of the method. Implicit Runge-Kutta methods, where the Butcher tableau is no longer lower triangular, but also include an upper triangular part, provide a remedy for this problem. However, this remedy comes at a cost. In order for every step to be calculated, a system of some algebraic equation need to be solved. And this, of course, is computationally much more demanding and is not very feasible in practice for larger problems. However, for sample test problems, or if you're very lucky with your problem at hand, this might be handy. The simplest implicit method is the so-called backward Euler scheme, where the Butcher tableau is now more full, in the sense that we have the same value of x, the x hat value in the expression here below, both on the left-hand side and the right-hand side of the equation. This makes the solution not a simple evaluation, but you need to solve the equation separately for every step now. And that, of course, causes more computational demand for calculation the solution. Let's consider a very simple example. Consider the two-dimensional nonlinear ordinary differential equation of this form given on the slide. So we have the temporal derivative of x1 and the temporal derivative of x2, and then this expression here. It might be easier to consider some solution trajectories from this problem. As you see, this problem has a fixed point at origin, which is an unstable spiral. You see the solution spiraling out from 0. And then a limit cycle around 1, which you see like the inner and outer solution trajectories spiraling towards. So now in every quadrant, I've simulated solutions. There are actually 6 solution trajectories in every quadrant, and the solution trajectories starting each quadrant are simulated by a different method. Basically the methods presented on the previous slides. If you now closely look at these trajectories, for example, the forward Euler method in the upper right quadrant, you see that it differs from the rest. And even though this problem should be completely symmetric and all the solution trajectories starting from different quadrants should be similar, in this case they are not. So now, for example, for the forward Euler problem, the step size is clearly too big. You see that the solution trajectories are not smooth and they tend to jump around a bit, even though they are not completely diverging. The classical Runge-Kutta 4, the fourth order Runge-Kutta method, and the Heinz method, which we briefly considered earlier, perform a lot better, but not even they are giving the completely same solution trajectories. And in this case, the implicit backward Euler scheme in the lower left quadrant clearly gives very stable and smooth solutions. Well, the practical differences in this case are not big, but if you would consider making the step size even bigger, the differences would of course grow.